Hello, anyone got try to tell us what you tried? So you tried? What have you done? Add add together. Okay, so let's try. So let's try some working here, right? So what's the working you can do? How to add? Add what? What do you add? En minus L. Oh, okay, absolute of Pn minus L and then equal to hmm, yeah. Huh? Don't know. Okay. Any others? Try. What have you tried? Tony, did you try? What do you get? Okay, you don't start from first, is it? What do you mean like this? Greater or equal to an? Yes. Okay, this is what we have. And then, sorry? Huh? All side. All side minus L. Okay, okay. So, okay, okay, I get what you mean. So this one is true, then if and only if an minus L is equal to bn minus L is equal to cn minus L. Like this. Okay, and then give absolute value to all of them. True. Give absolute value to all of them. Is it true that A less than B implies absolute value of A less than absolute B? No, right? Yeah, only both larger than 0 or both negative. The both negative. Or negative doesn't work, right? Ah, yeah, yeah. Only both positive. Hmm. Yeah. Mm-hmm. 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 Okay, so you saying that if Cn minus L less than epsilon, this implies then Cn minus L is less than epsilon greater than minus epsilon like this. Okay, so you're gonna use this for your Cn minus L to bound your Cn minus L. And minus L less than epsilon. And then, right? Similarly, you can do it for An, right? So An also bounded below by some negative epsilon. Then Bn minus L is less than epsilon greater than minus epsilon, which means it's less than epsilon. Okay, good. Okay, you found that Bn minus L is less than epsilon. But Do you still remember to do one thing? To prove convergence, what do you need? For every epsilon, you need to find the n, capital N. Okay, so where's the n here? Where is the n involved here? Where's the capital N involved here? Which part you need the n to come in? When you bound Cn minus L and An minus L within epsilon gap here. Okay, so here is the place you need n. Okay, so right. So here, so this step here we have n epsilon c. Okay, and then so this happen when n is greater or equal to n epsilon c. Here happen when n is greater or equal to n epsilon a. Okay, are these the only n we need to consider or not? There's one more, right? Which one?
Make sure that Bn is between A and
Yes, so we have another one to make sure that this inequality is solved. So actually at the very first we have this Bn already. Okay, so actually how many n we are considering here? 3n. Okay, we have 3n to consider here. So how to pick among the three? How to pick among the three? We need to pick maximum. So we need to choose our n epsilon to be the maximum of the three. Okay, why pick the maximum among the three? So yesterday I put some add-on to my notes. Okay, for example, this example here, right? Pick the maximum of 2. Can everyone see or not? Okay, so why pick maximum among the 2? So let's see you have these two sequences here. Okay, AN and BN. You can see that BN decrease faster than AN. Can you see? BN decrease faster than AN. Okay, so if I pick some epsilon, let's say epsilon is 1/4. Okay, you see, if I look at this epsilon get around my limit here, so limit here should be 0. Quite obvious, right? The limit should be 0. So along this gap here, you see, which term go into this gap? Okay, which term of the two sequence go into this gap here? Okay, you see. So the first AN, right, is, you see, 1, 2, 3, 4. Only the fourth one comes into the gap. 1/4 gap. But how about BN? 1, 2, 3. 3 already coming into the gap. Okay. Does it make sense? So you need to pick the maximum one so that both of them lies inside the epsilon gap. Okay, if you pick 3, the first one haven't go into the gap yet. Okay, so you need to pick the furthest one. Does it make sense? You need to pick the furthest one. 4. Okay, if you pick 3, you see, AN haven't come into the gap yet. Still on the boundary line. Okay, you need to make sure everything is lie inside the gap of 1/4. Make sense or not? Okay or not? That's why we pick maximum. Okay, hey, can someone close the door? In the aircon go. Thank you. Yeah, makes sense. Okay, try and study these examples again. Better. Okay. Yeah. Any question or not on this example? Looking at the epsilon and then finding the which end that works. Okay. Okay. So I put this as an add-on in the proof. All right. So let's continue. Sure. Where is it? Okay. Okay. So yeah. So try and turn this into a proof, proper proof. Okay. And then let's continue with theorems. So in the lecture, right? So maybe I will skip how to use this theorem, but I will still insert examples into the notes. Okay. If you don't understand the examples, you can raise in the class and then we can go through. Okay. Because how you use it actually is covered in calculus 2. So we can skip as much as possible so that we can spend more time to learn how to prove. Okay, so let's go back a little bit for yesterday. So yesterday where we stopped? Yesterday we stopped at the nested interval theorem, right? Okay. So there's one condition here is really crucial, okay, in the theorem, which is the interval is closed and bounded. Okay. Let's say if I turn it into a closed one, not a closed interval. Okay, does this proof still works or not? Okay, you can ask this question. Does it still work? Okay. The claim is it won't work. Okay. So you could imagine that there are nested interval by this in here. Okay, how do you imagine this in? You have I1. What is I1? 0 to 1. Okay, so there is 0 to 1, let's say. What is I2? 0 to half, but not taking the endpoint, right? So 0 to half is maybe around somewhere like this. 0 to half, okay. 1, 3, I3. So 0 to 1 over 3. So you can see that we still have the nesting effect here. Okay. And also the length is getting to 0, converge to 0. But you cannot find a unique point that lies in every interval. Okay. But you cannot find. Okay, you cannot find a unique point that's lying in every interval. Can you see why or not? Because if you are an analyst, you need to be very precise. If cannot, you need to say, show me why cannot. Okay. So my claim is you cannot, there doesn't exist a unique point x in in for on. Okay. So as an analyst, you are very precise. You should be very precise. So you say cannot. Okay, let's say can. Let's say can. Prove it. So suppose you can. Suppose you can, right? Okay. Suppose you can. Okay. Meaning what? There exists an x, okay, which is in in for all n in n. Okay. Suppose you can. In particular, this point here is in where? It's in real number. Where is in real number? You want to get contradiction already? How to get contradiction? Suppose, yeah, suppose already. Suppose I have a x, again in in for all n. Then what? Sure, how to find it? Hmm.
Bigger than 1 over n.
What is that? Yes, Archimedean property again. You see, here got 1 over n, trying to hinting the Archimedean property already. So the whole course is trying to play around with this thing. Okay, Archimedean property. So by Archimedean property says what? Actually, it's a result of Archimedean property, right? So by Archimedean property of R, there exists a capital N in N such that 1 over N is less than X. Okay, so X is not in the interval from 0 to 1 over N. contradiction. Okay. Sense. Hey, you need to draw a picture. Picture here. What's the picture here? You got a x, you got a 1 over n here, and then you got a 0 here. So can you take this interval? Right. So this is my in here. Okay. So whenever we draw this inequality, please in your mind pull out your real number line. Okay, pull the real number line out. Okay, and then plot it. Where is x? Where is 1 over n? Where is 0? Okay, make sense? So this is another way to talk about Archimedean property. Okay, does it make sense? Yeah. Question? Any question? No. Okay. So whenever we talk about real numbers inequality, try to pull out a real number line in your mind. Okay, and then plot them. Which one is further away? Which one is closer to 0? Okay. All right. So let's continue for today's topic. Okay, now we want to talk about subsequence. Let's talk about subsequence. So let's done with this part here. For definition, let AN be a sequence. A subsequence of AN is any sequence obtained by omitting some of the terms of AN. Okay, that is a sequence Bn. Okay, so subsequence is another sequence. Okay, we call it Bn. It's a subsequence of AN if, okay, so how we pick out this subsequence, try to be very precise here. There exists an increasing function. Okay? Increasing function. So what do we do with this increasing function? We call it J from n to n, such that the Bn terms here is equals to Ajn. Okay. So let me illustrate this to you. So once you have this definition, right, you should have some imagination. Okay. So let's say, what kind of a function is an increasing function here? Let's say we take n to 2n. Is it increasing? Increasing or not? Increasing, right? Okay. So let's say my n is 1 over n for all n. Okay. So we like 1 over n a lot. Let's keep using it. So 1 over n sequence. So what is Bn here? Okay, which is equal to Ajn. What is this? Is this? It's simply 1 over 2n. Okay, so let's draw this thing out. Okay, let's draw this thing out. Okay, maybe not draw first. Let's just list them out. It's easier. So let's say an, right? An. How does an look like? So an, inside an you have 1 half, and then 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, 1/9, 1/10, 11, 12, so on, right? Okay, dot dot dot. So what is Bn here? Bn here is picking, for example, one. So for example, we're picking 1, 2, 1/3, 1/4, 1/6, 1/8, 1/10. like that. Okay, so we are picking a subsequent out of it. Okay, so inside my Bn has what? 1/2, 1/4, 1/6, 1/8, and then 1/10, and then so on. Okay, okay or not? But we rename this. Okay, although this one is like this is A2, A4, A6, A8, A10, right? But we rename it to be B1, B2, B3, B4, B5. Okay, so we take the subsequence and then we make a new sequence. Make sense or not? This is this line here. Bn equals to Ajn. Okay, you see, B1 equals to A 2 times 1. Okay, B2 equals to A 2 times 2. Does it make sense? Okay. All right. So the result here is like this. Oh, proposition. So can we say anything about subsequence of a convergent sequence? If a sequence converges, okay, then every subsequence must converge to the same limit. Okay. So the result is if a sequence converges, then every subsequence, no matter how you pick, okay, the subsequence, it also have to converges and converges to the same limit. So how do we prove this? Goal. Okay, when we say proof, okay, you should ask what's the goal? What's the goal here? What's the goal here? Every. No, go. Just go. What's our goal first? I don't ask for recipe yet. Every subsequence must converge to the same limit. Okay, so what is same limit? Limit of the original sequence. Okay, this is our goal. And recipe very easy. Just one thing. The original sequence converge. So you see, you want to show for every subsequence, right? Universal quantifier again. So you need to start with any subsequence. Just start with any subsequence. So let's put our goal first. Okay, whenever people say prove something, okay, what is the thing you want to prove? Very important. Okay. So we want to show that every subsequence must converge to the limit of the original sequence. Okay, so we want to show for every, so we just start with any. Okay, so let Ajn be any subsequence of An. Okay, and let's say we should say that let An converge to some limit L. Okay, as n go to infinity. And then let Ajn be the subsequence. Right. So converge means what? For all epsilon, you need to find a n such that Ajn minus L is less than epsilon. Good. So this is what we want. But what do we have? By assumption, what do we have? What do we have? We have capital N for An. Good. So let's write down. So we need to fix epsilon also, right? So just let epsilon greater than 0 first. Okay. Wait, let me move things down. So let me be precise here. So here, in other words, for epsilon, whenever epsilon greater than 0, there exists an n epsilon in n such that ajn minus L for all the terms Jn greater or equals to n epsilon implies the absolute value of Jn minus L is less than epsilon. Okay. So this is what we want to show. So we let epsilon greater than 0. So by assumption, we know if we fix epsilon greater than 0 after fixing epsilon greater than 0, okay, an converges, right? So there's a God-given natural number here. So there exists positive, sorry, there exists n. So let's name this n here so that we don't confuse. So let's name this n for a. Okay. There exists a natural number a. Natural number a depend on an, depend on epsilon in n, such that for every term behind n epsilon a, we have that the absolute value of an minus L is less than epsilon. Okay, we have this. So how do you use this assumption here, okay, to get the inequality for your subsequence? What n epsilon you need to pick? What's the n epsilon you need to pick here? Okay. So what kind of n you need to pick? N epsilon you need to pick here. So you should imagine in your mind, okay? You should imagine in your mind. So how do you imagine in your mind here? So you need to turn this inequality into picture. Otherwise, you don't know what are they doing. Okay, so let's say an converge to L. Okay, so what does this mean here? So let's say this is L here. So an converge to L. Maybe do something like this, alternate, alternate, alternate. Converge. Okay, there's an epsilon gap here. Okay, so you need to imagine an epsilon gap. Imagine an epsilon gap. Okay, so you see, there are a lot of things going on here. So to go into this epsilon gap, right, there exists an n. So what's this n here? This n depend on epsilon, depend on your sequence. Let's say this is the n, right? Because after this n, everything is within the epsilon gap. But you want to show it for ajn here. What is ajn? Ajn is just subsequence. So subsequence, the term of subsequence also come from the original sequence here, just by maybe omitting some of the point. Okay, so how do you make sure that the term in the subsequence is within epsilon gap of L? Sorry, maximum of what? N and what? And n epsilon and what? And this one. This is what you want to find, right? Okay, because you want to prove it. And this one is given. Okay, this one want to find. This one given. Yeah, just take the same number. Just take the same number. Does it work or not? If I just take the same number, does it work? You believe it does. You need to prove it. Okay, because you're an analyst. You cannot just believe. Okay. So if n is greater than n epsilon, means what? Okay. So should I do like this? So if for n greater equals to n epsilon a means what? Means that Jn is also greater or equal to Jn epsilon a, which is also greater or equals to n epsilon a. Why? Because J is increasing. Because J is increasing. Only increasing function can keep the inequality. Does it make sense or not? What is the increasing function? Yesterday we introduced non-decreasing, right? Okay. So non-decreasing could be okay. So let's recall. So a function is non-decreasing, then f is non-decreasing if what? If f uh, we introduce function. Yesterday we introduced sequence, is it? Sequence non-increasing. So function, how is it function increasing? So let's just get it. Okay, I think we did it in the assignment last time. So function is increasing if what? If x less than, do I want less than equal here? Less than y. Okay. Okay, let's do it less than equal to y, and then do it for strictly increasing next time. So if it is increasing, if x less than y, then fx is less than equal to. Okay, this is what we want. Okay. So this actually mesh up the intuition, right? For example, ex is increasing function. Right? So if you have further x here in the real line, the y axis also go up, increasing. Okay, if x less than equal to y, then fx is less than equal to f1. Make sense? Okay. So this is increasing. So once you have this, are you good or not? N greater equals to Jn, okay, which is greater equals to n epsilon, implies the absolute value of Ajn is absolute value of Ajn minus L is less than epsilon. Okay. Yeah. How I know that n is larger or Jn is larger? How I know that n is larger or Jn is larger? Here. So this say again, what are you talking about? Oh, am I doing stupid stuff here? For n. Wait, I think, am I? Okay, so I think I need to change this n here. This is Jn. Wait. So, wait, okay, let me see. Okay, so, all right. So you see, here. So here at the end here, we want Ajn, right? Okay, so we need Jn greater or equal to J. Like this. Okay, and just now have an extra n then. Okay. Just now, what is your question again? Ah, yeah. Yeah. Jn seems larger than n. Jn seems larger than n. No, not really. Not really, not really. As long as you keep this inequality is enough. As long as you keep this inequality is enough. Okay. Mm, yeah, as long as you keep this inequality is enough. Because I can shift the EX down, right? It's still increasing. I can shift EX down, still increasing. Does it make sense? I can shift EX down, still increasing. Okay, no. Mm. Maybe one question you can ask here, why this part is not n, is Jn? You can ask this question. Why? Uh, but if you first time seeing this proof, right, you'll tend to like repeat what we have did before. What we did before is we will rewrite this as some an, right? And put n here instead of j of n, right? But because this is just a label here, just a label. So we could label like this. Okay, we could label, for example, like bn, for example. We can label as bn because just now we write that bn equals to aj. Okay, and then in this case here, you could say that uh, n is greater or equal to aj. Yeah, you could do this as well. It's just a naming. Okay, it's just a naming. Okay. Yes. Sorry. I think this one. Wait. Let me fix something first before we go on. So let me fix. I think this one is just this. Okay, continue. Yeah, you can continue. What's your question? Ah, YJ, where? This one. This one. Previous one. Okay. Okay. Oh. Oh. Okay. Oh, why is this true, huh? Is this true or not? Let me think. Oh, this is what you said just now, right? Is this true? Mm. Do I need this first? Okay, let me think. Let me think. Think. So this might not be always true for increasing function, but ours is a sequence. Let me think. Let me think. Let me think. Um. So is this always true or not? It's always true. Increasing function. How to show this is true? Let me think. Um. So increasing function. Is a function. Mhm. Greater than n, greater or equal to n. So let's prove this. Okay, let's prove this. So what lemma here? Huh? Which one? This one? You mean this? Increasing function. I think. How to prove this? The It's quite obvious, but how we prove that? Or suddenly how to prove this? We should be able to say suddenly not on top line. So let's think. What time is it? Okay, let's take a break to think about this. Okay, then we'll come back. 10:09. Yeah, 10:09.啊，也可以，只是我忽然间想不到了。嗯，
你接一局跟前跑过比这个 M 下来，对，其实你在领的是八局少一级。
但是假设我在零那边，我就是选那一个嘞，然后其他的我在做。啊，so 我想一下，忽然间想不出。 哪一个？第二结果，Yeah， yes yes yes，对，这个要换，你说这个哈，这个要换成这个什么？我本来写等于啊哈，对对对对对对对对对对对对对对对对，不一样，应该要大于等于。如果这边是对的话呢？如果这边是对的，如果这边是对的，对不对？讲一下啊，哪一个哪一个？这个这个应该要大于等于，因为这是从上面来的，只是从上面搬上来的。诶，有可能等于，但是说也有可能大于，有可能大于，也有可能等于，也有可能大于，也有可能等于。pick 啊 pick 等于 Jn epsilon x。你说选就是选，可以，你也可以选哪一个，你也可以选哪一个，你可以直接选大的，但是小的也够啊，因为你知道你前面已经 conversion 嘛，如果你再 consider 远一点，它还是 conversion 嘛，你也可以直接选那个比较远的那个，懂什么意思吗？啊，你可以选远的那个，我现在是选近的，这个近的已经 conversion 了，但呢代表后面的也 conversion，但是你说你要 plug 在 Jn 加 epsilon a 那边也可以，因为那边啊，但是现在问题是回来这个就是来这个，这好像很，我觉得是我突然间想不到，有2分钟，那我的 inductive proof start 就我们，你看啊 base case 一定要对，我不可能把它送回去。OK，inductive proofs，inductive hypothesis，OK，肯定对。你看我要 prove 的是这个哦，现在我有这个嘛，然后这一个可以用 increasing 来做那个，这个等于 n 罢了，我不能够这样理解。最多等于多少？因为啊，你想一下啊，subsequence 的概念是这样：A1、A2、A3、A4、A6嘛。我选一个，我最多选一模一样哦，不会变。但是我可能第二个不要选，第三、第五个不要选。你看啊，这个是我的 B1，这 B2、B3，肯定是肯定是大过的。嗯，怎样说？诶， 啊 n 加一大过，然后 n 加一大过等于 n 加一，可以啊？为什么？哦嗯，hello hello 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 hello. Okay. Regarding this question, right? I think it's obvious from how we construct the subsequence because if you have a sequence, right, and you omit some terms from your original sequence and then you pick it as a subsequence, right? You can see that the difference here is like uh, greater or equal to 0. Okay, so here is like J1. Oh, okay, so J1 should be put here. So J1, J2, J3, J4 here. Can you see or not? So you can see that J1 is greater or equal to 1. J2 is greater or equal to 2. J3 is greater or equal to 3. J4 is greater or equal to 6. Okay, but somehow I cannot construct this proof. So my statement is like this. So let's say we put this statement like this. If J is increasing, right? Okay, we want to show that Jn greater or equal to n for all n. This is our observation just now. Okay, this is our observation. We want to show that Jn greater or equal to n for all n in n. So my best case is like this. J1 has to be greater or equal to 1. If J1 is less than 1, what is it? What is it? Nothing. So it's, yeah, doesn't exist. Okay, so it's not a proper map. So J1 must be greater or equal to 1. Inductive hypothesis, suppose Jn greater or equal to n. Okay, and we want to prove that Jn plus 1 is greater or equal to Jn plus 1. Okay. So since I know that n plus 1 is greater or equal to n, I can use the increasing function property to state that Jn plus 1 is greater or equal to Jn. And I can use inductive hypothesis again to say Jn greater or equal to n. But I still haven't pulled out my n plus 1 yet. Quite annoying. So how? Okay, so if it is strictly greater than n, then it is n plus 1. Okay, then we are good. So here greater or equal, two things, right? Either greater or equal. Okay, if this thing is greater than n, again, then we are good because greater than n meaning greater equals to n plus 1. How about equal here? Any contradiction or not? If it's equal to n. Okay, so let me write down. So this is like, we are like, I also don't know, you also don't know, so we have to do from scratch. Okay, so let's do from scratch, right? So case 1 and case 2. So there are two cases here. Case 1, Jn plus 1 greater than n. Case 2, Jn plus 1 equals to n. Okay? Two cases here. If it is greater than, strictly greater than n, this is good because strictly greater than n just means that it is greater or equal to n plus 1. Agree? Agree or not? Strictly greater than 2, you must be 3, 4, 5 because our natural number range is like get with 1. But how about equals n? Any contradiction here? No? If Jn equals n. Wait first. Okay, so what's the problem? Any problem here? If Jn equals n. If Jn equals n, and Jn plus 1 equals n, no. I mean Jn could be strictly greater than n, right? So okay, let me write like this. So if Jn equals to n implies that Jn plus 1 is n. Correct or not? If this is equal here, right? This will implies that Jn plus 1 equals to n. Sorry. Okay, wait. A bit confusing. Wait. Let me reconstruct my thing again. Okay. So so we shouldn't write like this. So let us restart again. So I think we are not precise again. So make things precise again. So what's the two cases here? Yeah. So okay, let me do like this. Okay, case one actually is not Jn, right? Actually not Jn plus 1, but Jn equals n. Sorry, Jn strictly greater than n. And then next one is Jn equals n. Okay. So if Jn strictly greater than n, this would imply that Jn plus 1 is strictly greater than n. Then we have this result just now. If Jn equals to n, this implies that Jn plus 1 is greater or equals to n. Correct? Okay. If Jn plus 1 is greater than n, we are good. Fair enough. But how about if Jn plus 1 equals n? Okay. If Jn plus 1 equals n, so this one is the first case, second case here. And also Jn equals n. Then what? Okay, I think this is good. This is very good. I think this is very good. Why is this? This is very good. Increasing function actually means that the function is 1-to-1. But here it's not 1-to-1. So if Jn plus 1 equals n, Jn equals to n means what? You pick n twice. You know, let me show you. Let me show you this now. What happened? If this happened, this means what? B3, I also pick this guy. You know, B3 I also put A3. Okay, so let me use another color. Okay, let me use another color. Okay, if Jn is n, Jn plus 1 also n, meaning you pick some number twice. But subsequent is not like that. Subsequence is like you pick the sequence and then you omit some of the sequence during the process. But you cannot pick a term twice. So you pick twice here. Okay. So I put here, since increasing, so we can prove, I think we prove it in our course or not? Increasing function is 1-to-1. Like calculus 2, not yet. Never. Forget already. Okay. So since increasing function is 1-to-1, this is a contradiction. So are you skeptical with increasing function is 1-to-1? I think we need to write it out. This one you need to write it out. Okay, so let's put this as a lemma. Okay. Yeah. So if this last case here happened, meaning you pick a sequence twice, but this is not what we define. Okay. Implied by what we know, what we define. Okay, no. a bit non-trivial, but should be intuitive. Okay, non-trivial, but intuitive, quite subtle. Okay, quite subtle. You need to show it. Does it make sense? Okay, so I think we will include this inside the notes. Okay, we will include this. Yeah, very good question actually. Yeah. It's not too hard, but just you need to write it out. Okay, it's quite subtle. You need to write it out. Okay or not? Make sense, huh? Okay, before that, we need to discuss about our assignment timeline. Okay, so I can agree to extend the assignment, but I want you to keep in mind there's another assignment deadline before we have an exam. So I don't want to like drag this deadline here, because once we drag this deadline, this will affect your preparation for your midterm. Okay, so you need to pick some date between here, but make sure you have enough time to keep the last deadline before we have exam. Is it possible? Okay, so next week, Wednesday is a holiday. Okay, so you need to decide whether you want to submit before holiday or after holiday. Okay, so that you won't affect the last deadline before the midterm. Okay, because I need to hand them back to you so that you can do preparation for midterm. Does it make sense or not? Okay, so can you decide you want before midterm or after midterm? For the before, can everyone agree before holiday? Okay, so before holiday there are 2 days, right? Monday and Thursday. So Monday you have a replacement with me, so you can ask question if you like about assignment again. Sorry, Monday night. You think Monday night? Okay, sure. Does everyone agree with Monday night or not? So that you have enough time to do the third one. Monday night. Wait, what? Monday night, Monday midnight. Yeah, so the last chance you ask me is during the replacement. Make sense or not? What 9号? 9号, this one is for the third assignment. Sorry? Second is around here, right? Should be tomorrow, right? Tomorrow is here. Okay, tomorrow is here. Next week is here already. And then next Wednesday is the holiday. And then we need to try and keep this deadline intact, because I need to mark, and then you need to study, and then exam here. Okay. 安排得明明白白。So yeah, the room here is here. So Monday or Tuesday, sorry. Monday we got a replacement class, right, for this Wednesday class. So Ethan just now suggests to have deadline on Monday midnight. So during Monday, you still can ask me question, right, in the class. So what do you guys think? Monday midnight, is it possible? Can? Okay. You 中意 midterm 可以再草稿吗？可以。Okay, midterm cheat sheet, yeah, cheat sheet. Like calculus 2 cheat sheet, double page cheat sheet. Okay, you can copy anything into your double-sided, but handwritten cannot use computer generator. Use handwritten. And please don't tap the sticky tab on the A4 paper. I got students do like that. You don't laugh. So don't take 3D only 2D 2D allowed. Okay, 2D allowed, no 3D. If you bring 4D can. Okay, I want to see 4D. If you can bring 4D, I allow. But no 3D, no 3D. Okay, 2D. Okay, can bring draft, not draft, cheat sheet, double-sided, handwritten. Okay, yeah. I will remind you again later. Okay. Okay, so everyone agree? 29 midnight. Okay, 23:59. 23. Okay, so you got a weekend to do, and then yeah. So last time, right? Last time they have a study group. If you guys want to join, right, you can message in the group for the assignment. Okay, and I will be present if you need my help. Okay or not? Yeah. Because I make this assignment very hard. You know why? I'm bad. Yes, I'm bad. I'm really bad. I'm the villain. I'm the Batman want to kill me one. So yeah, you can think of me like that, but I still want to say something. So I really want this knowledge to pass down in Malaysia. Okay. So I want you to learn all this, not just learn. Actually, I hope for more. Okay, maybe you think I'm too ambitious, to ask too much, but I'm like that. Okay, I don't want to deny. So that's why I asked the student council to come up with this Med Health Center by med student alone, not the master one. Master they have one every day 1 hour, right? Okay, if you can go, you also can go for help. But I want to start our internal one. Okay, you go and teach your junior. Okay or not? You go and teach your junior. Okay, so that this knowledge can pass on in Malaysia. I can tell you that it's within handful of people know this thing. Handful, you know what is handful? 这个手指可能数得完 that know these things. If you know, then you are one of the 10个手指. You get what I mean or not? So this knowledge is a very precious one. Sometimes you use money also you cannot buy one. 不要以为你付了很多钱给厦大，你会得到这些东西，不会的，不会，不可能，这是要看老师的。你再多钱呢，你不会就是不会。对，我是没有看钱的，我跟你讲，我看钱我不会来这里教书的，真的。我老师跟你讲啊，去对面教书啊，还有8000块，教的东西还比这边简单，真的。所以，我就跟那些学生讲，如果你不喜欢我，你就不要讲我，因为我做的东西我不是在，OK。And 我是准备帮忙你们的，所以如果你们真的有问题，你们在 D6 做也好，在 LY3 也好，我能够去的地方我尽量去。OK，所以我也是住在学校也比较方便。OK，所以不要跟我过不去啊，千万不要跟我过不去，因为你跟我过不去的话，我也可能会跟你过不去。真的真的，我很老实跟你讲，真的真的，因为我不是一个人，我不是一个喜欢玩玩的人。如果我做一个东西，我要做到我觉得好，可能你会觉得我的程度太高啊，太严啊什么，那这个就嗯，因为我已经花很多时间在这个东西上面了，我不要马马虎。别的老师我不知道他怎样想，但是我觉得我变 OK。Yeah，我对于这些东西是蛮 serious 的，我可能会出错啊，可能我会，把我会改。OK，呀，所以我希望你们如果已经学会了、学好了，我也希望你们这样子去带其他不会的人。OK 啊，Yeah。So if in this case, then we fix 29 midnight, okay, for the assignment 2 extension, and then we will fix either 9 or 10 for the assignment 2. Okay. Okay, last 30 minutes. 30 minutes. Let's do the last theorem. Okay, let's do the last theorem. Bolzano-Weierstrass. Sometime in the book, you will see that this is a sequential compact theorem, but I don't want to introduce sequential compact in this class, and I won't use it. I won't use this word. So I don't want to talk about sequential compact. But if you look at Prof. Theonox, they introduce what is closed and compact in a general sense, but I won't do it in this course. Okay. Even if we're using the property, I won't speak about this term here. Okay, unless you come to a general topology. All right, so Bolzano-Weierstrass. Okay, here is a two-person name here. Okay, so in particular, this is a very good research topic. Why this two-person come up with this theorem here? Why in that time they need this theorem? Okay, go and try to search for it. So what's this theorem here? This theorem says that every sequence, okay, AN, in a closed, bounded interval, CD, has a convergent subsequence. Bn, okay. So it converge, right? Converge to where? Converge to somewhere inside the closed interval. CD, okay. Where CD is in R and C less than D. Okay, so this is talking about the interval. Okay, so think about this question again. Every sequence, okay, what kind of sequence? Sequence in a closed bounded interval. Okay, so meaning the interval is bounded and it is closed on both sides. And you can extract a subsequence which is convergent. Okay, and then converge to a point of CD. Okay. Does this make sense to you or not? How to find this convergent subsequence? Okay, how to find this convergent subsequence? Okay, actually, there's one tool you have, right? If you have a decreasing nested interval, okay, then you can find the limit. Correct or not? Okay. Can I produce some nested interval here? Okay, so how do you imagine this terms here? So when I talk about interval, right, pull out your real number line again. Okay, pull your real number line out. And then there's sequence inside here. So sequence like what? Maybe let's put some dots here. So maybe A1 here, A2 here, A3 here, A4 here, A5 here, A6 here, A7 here. Maybe jumping around. Okay, jumping around. Okay. But it says that there's a convergent subsequence, means what? Okay, maybe you pick A2, maybe you pick A4, maybe you pick A5, A7, and then you pick such a way that the sequence will converge to one point. But how to construct this convergent subsequence? Okay, how to construct this convergent subsequence? Okay, how to construct the conversion subsequence here. Okay, we are trying to use a nested interval theorem here. Okay, so we will first introduce something called the pigeonhole principle. You know what the pigeonhole principle is? What's the pigeonhole principle? If you had n pigeon, right? If you have n minus 1 pigeonhole, then one of the pigeonhole must have at least two. At least two, right? Okay. So you can generalize this. Let's say your pigeonhole, the number of pigeonhole is strictly less than the number of pigeon. Then also at least one of the hole must have at least two. Okay. But we can generalize more here. So if there are infinitely many objects placed into finitely many boxes, then at least one box has infinitely many objects. Does this make sense? If the second line is not true, meaning what? None of the box has finitely many objects, but you only have finitely many boxes. So finite times finite, you only have finite. So you don't have infinitely many. So meaning you have infinitely many objects placed in finitely many boxes. One of them must be infinitely many. Okay or not? Does it make sense? Suppose this is not true. Okay, control positive. None of the box has infinitely many objects. So meaning all of them are finite. Finitely many objects times finitely many boxes. You only have finitely many objects to start with. Okay, so one of them must be at least infinitely many. Okay, not that our sequence doesn't end. So we have infinitely many terms in my sequence so that we can talk about the tail of the sequence here. Okay. So what can we do? We want to make a nested interval, right? Okay, how do we make a nested interval? So first we can divide the interval, okay, CD, into two close bounded subinterval. Okay. How do we do this? Let's do it with equal length. Meaning I cut in the middle. I cut it in the middle. So I do it from C to C plus D over 2, the midpoint. Okay, and then union C comma C plus D. Sorry, should be start from C plus D. Yes, correct. So C plus D over 2 to D. This is equals to C to D. Okay. We cut it into two things. Two subinterval. Two subinterval meaning what? By pigeonhole principle, right? You have infinitely many things put inside this interval here, and then I cut it into two. So meaning at least one of them must have infinitely many things. Correct? One of them must be infinitely many. Okay. So what do we do next? So I'll say at least if both of them are infinite, we just take one of them. So at least one of these contains an for infinitely many n. And then we just pick one. Okay. If both of them are infinite, just pick any one. Okay. Once you pick it, you can call it. Let's call it and call it C1 D1. Okay, C1 D1. Okay, we do C1 D1. And what can we do? We can build a subsequence here. So how do we build a subsequence? So we choose B1 to be AJ1. So what is AJ1 here? Okay, where J1 is the smallest value such that AJ1 is in C1 D1. Okay, can you imagine this or not? Okay, so let me do an example, right? So they are like A1, A2, A3, A4, A5, and so on, right? In C, D, N here. Okay, so maybe you split into two parts. Maybe A1 here, A2 here, maybe A3 here, A4 here, A5 here, maybe, right? And A6 also here, maybe. But let's say the infinite one stay in the second one. Okay, then we will pick the second one to be our new interval that has infinitely many terms. Okay, and then how I pick this B1 here in this case, I pick such that J1 is the smallest value. So which one has the smallest value here? 2, 5, 6. 2 is the smallest value. So my second term for my so my first term of my subsequence is just A2 in this case. Okay, so this is some example. Does it make sense? Okay, I pick the smallest one. Okay. 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 So what I do next? So I repeat the process. I repeat the process. So I divide. So now subdivide again. Subdivide the interval with infinite terms C1 D1s, okay, into two halves, okay, in the same way. So we divide it into C1 plus D1 over 2 union with C1 plus D1 over 2. Then we subdivide this. Okay, and then one of them has infinitely many terms. Okay, then let C2 D2, okay, be one of the half which has infinitely many terms. Okay, of A. Then we will let the second term in my subsequence to be what? To be the smallest number again. Okay, but maybe your first term still in there, so it must be a smallest number which is greater than J1. Okay, such that AJ2 is in the interval with infinitely many terms. Okay, so we continue this way. Okay, so continue this way. What can you imagine? What can you imagine? What can you imagine if you continue this way? Take the infinite one, cut half, pick one term. Okay, the smallest one, cut half, pick one term, cut half, pick one term. So what do you produce? So we actually produce a nested sequence. Okay, we actually produce a nested sequence of interval which we call CNDN, right? What's the length of this? What's the length of this? We keep taking half. Sorry? Say it louder. Converge to 0, right? But what's the length at every level? Is you're taking half of d minus c, right? So the each level you take is 1 over 2n. Okay. And these interval, right, each of them contains infinitely many points. Correct or not? This is how we make the choice. Okay. Many terms of the sequence. And we also pick the subsequent, which we call an. Sorry, which we call bn. Such that bn is in cn, comma a. Make sense? Okay. So now we have nested interval, closed bounded interval, interval that converge to 0. We can use the nested interval theorem. Okay. So what does the nested interval theorem say? There exists a unique point x in Cn dn for every n private n. Okay. Yeah. Okay. And what's this x here? What's this x here? L. This is the limit. We want to show that actually, we want to show that this S is actually the limit of the subsequence I produce. Want to show this. So meaning for every epsilon, there exists an n such that Bn minus L minus x is less than epsilon. Okay. How we do this? How we compute Bn minus x here? How we compute this? Yeah. It's an epsilon around. Sure. I mean, how we bound this guy? We want to show this is less than epsilon, right? How to bound this guy here? So you should in your mind, right? You should in your mind you think CD, okay, and then C1 D1 maybe like this, and then C2 D2 maybe like this, C3 D3 like this, right? Okay, and then S is maybe in between here, okay. So B guy is somewhere like maybe B1 here, B2 here, B3 here, something B4 here, okay. So the difference between Bn and X here, how is it bounded by? Okay. Actually, this B is lying between Cn and Dn, right? So this difference here must be at large what? At large Dn minus Cn. This is the endpoint where there lies. Okay. But we know the length of this. We can control this length. This length is what? 1 over 2n d minus c. So can you find an n such that epsilon is greater than this guy? Can you do that? So we just choose n such that n epsilon such that 1 over 2 to the n epsilon times d minus c is less than. Cannot. Yeah. 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 We can. Or do you want me to show you like really precise? Can or not? Can find this n or not? Can or not? So this implies what? 2 to the n epsilon is less than epsilon over d minus c. Okay. And then we need to make sure that 2 to the n epsilon is greater than. Sorry, we're finishing soon. Thank you. So d minus c over epsilon, right? And then we didn't define this long thing, right? So how do we go about it? I mean, sorry. So how we go about this? So we're going to find this n such that this holds, right? So let's see how we do this. So by Archimedean property, right, we can find an m here. So let's put an m here. Okay. So 2 times 2 times 2 times 2 times 2, how many times greater than this natural number here? You do that calculation. Can you do that? You get what I mean? What you need to solve here. So by Archimedean property, you have a m which is in the natural number that is greater than this epsilon guy here. Correct or not? So this is by Archimedean. But you want to turn into some 2 to the power of some natural number, right? So the lemma here is for every natural number n, okay, there exists a natural number n such that 2 to the power m is greater than n. Okay, prove this. Then you will know how to find. Huh? Similar, a bit similar, a bit similar. Huh? Yeah, for all n, you need to find an m such that power of 2 to the m is greater than n. You can find this, right? For example, I give you 100. What is the m? 10 a bit too much, but still can. 5, 4, 6, I think good. Yeah. So you need to produce a systematic way to if you say there is this one. A bit similar. Can just this one, so Larry suggestion, Larry suggests you go and try this and then prove by induction. Choose a very big one, 2n. Prove by induction, Larry said. Try.